Okay, chapter 4, we look at defect and imperfection in solids. So we'll look at solidification of metals. We'll look at imperfection, we call it defect. Then we go for porosity and segregation. Okay, now we'll now focus on metals. When we melt the metals, and then we let the metal to cool down. So when metal cool down, it start to form solid phase. So it forms the metals go into solidification with a few steps. First, it start with the little dot in the liquid. So that little dot is called nuclear. And then the nuclear will start to grow. It grow into crystal. So as all these crystal become bigger and bigger, the crystal will crush to each other. But crystal and crystal, between the crystal, we still have a hole, still have a gap. So that gap between crystal is called grains or boundaries. It's called boundaries. Okay, so from nuclear form into grain, grain grow bigger, and then when fully solidified, then you will see the boundaries between the grains. So when you look under microscope for solid metals, you will see some structure like this. So you see all these layer, all these boundaries. Okay. Okay. So there are two types of mechanism that contribute to the nucleation of solid particles. Means the development of the little dot that you see in the first diagram just now. So there are two mechanisms. One is homogeneous, and another one is heterogeneous. So we look at each one of these. What is homogeneous and what is heterogeneous? So homogeneous, normally they are formed when you have a pure metal. Pure metals. When you have pure metal means they have the same element. So same element, you know that metals, when they cool down, they shrink. Right? Metal, when you warm it up, give it temperature, give it energy, it will become liquid. So when you have pure metals, then they cool down in an equilibrium freezing temperature, and then then they form homogeneous nucleation. So what usually when you talk about homogeneous or pure metals and process, so we look at a term called undercooling. So you look at the diagram here. So let's take aluminium. So aluminium, the maximum undercooling is 130 degrees Celsius. Right? So this temperature for aluminium, they will form a homogeneous nucleation. Right? And then the nucleus, we will try to quantify it. So there's one term called critical size, where the little dot just now becomes stable and start to grow bigger size and bigger size. Right? The rest you read, huh? Embryo, this one, embryon, is size below critical size, means not stable. Size that not stable is called embryon, and more than the critical size is called nucleus. Why this term is important? Because when it comes to your assessment, you're given a chart or a temperature, then you try to analyze the critical size. Then once you find the size through your calculation, then you can explain whether it is a critical size or it's an embryon or it's a nucleus. Right? So from this table, just now we talk about undercooling temperature. Then later we'll talk about energy. We have surface energy and heat of fusion, both in joule per cm square. One is cm square, one is in cm cube. Surface energy is more on square area, and heat of fusion is more in a volume. So this one I just mentioned just now. So for energy that involved in the nucleation, so it look at volume free energy and surface energy form. So if you look at volume free energy, it means it tell you the transformation liquid to solid. Because of volume, you can quantify, you can see whether it's a solid or liquid solid. However, the energy will tell you, surface energy will tell you that how many energy to form a new surface. New surface means it will grow bigger and bigger. Let's say for lead PV, the rest you read. So for lead PV, if it's cold below its equivalent freezing temperature, the driving energy, you look at differences in volume energy, or we use delta G. Delta G sub V means in the volume. So you look at this lead PV. Undercooling is 80. Surface energy is 33, 10 power negative 7. And heat of fusion is 28. So if you compare PB and aluminum, right? So PB is more easily to change into liquid compared to aluminum. You see the energy needed is much lower for lead compared to aluminum. Okay. So we start to develop equation for energy. Again, symbol we use for energy for nucleation means to start to grow into bigger size. Delta GV. We start with the sphere nucleus because we are assuming we are looking at the pure metals, and the metals that form, we start with the complete sphere. So complete sphere radius, the energy change will be you take the volume of the sphere over 3 pi r cube times the energy. Energy here is in the joule over meter cube or cm cube. It is in the volume term. So these are a few microscopic images. So they have a few types. So we are looking at the first type, spherical nucleation. So you have a splat cap, open porosity. Porosity means hole. So there will be a hole. You observe a hole on the nucleus, right? Or nuclear. Then elongated means it's like pulling two ways. Broken means chip off. Agglomerate means they have a loss of molecule that they combine together. Agglomerate. Huh? Irregular means you don't see a specific shape. Satellite means there is a extra extra element around the body. Then there's a graph that tell you on the energy. So how to read this graph? On the left hand side axis is the energy axis. There are three center, and then go up is positive, go down is negative. X-axis is the radius of particles. As you can see from the blue curve here, if you need to grow the nucleus, you need to grow the metals, solidification, you start from small one until big one. So you can see there's a curve. This is where you get the critical size. Okay, so you have one peak of the energy, which is total energy of change. You get a peak, this one. So before this, I think in chapter 2 or chapter 3, you see there's a repelling force and attraction force. So this one is in energy. So the top one will be retarding, means repulsive energy. This one negative is a driving energy. Okay. Else I need to mention. This curve on the peak of the energy, you bring down to the x, this x or r star, this is the critical size. So as you move forward, the radius will continue to grow, but the energy needed will drop because it's already reached a stable size. It just need to continue to grow. Okay. Again, just now we define the definition for embryo and nucleus, right? So size that below R star we'll call embryo. Size that bigger than R star is called nucleus. Right? So the lower curve is negative quantity. Upper curve is yeah, and so on. You read from the slides. So you read. So there is an equation to calculate or analyze the surface energy, give you by 4 pi r square, and then gamma. Right? So you know the surface of a sphere, you can calculate by 4 pi r square, and you multiply by the surface energy, so you get the energy needed for the surface. Whereas you read, total energy is the combination between the volume free energy and the surface energy. So you combine the two equations, right? So this is the equation for the first equation for today. You have the free energy to form your nucleus. So reversing back to the previous one, you see there's a table. This table will help you to calculate delta GT. All right, you have the surface energy, you have the fusion energy. Okay, so this is the first equation for today. To calculate the free energy needed for nucleation. Homogeneous nucleation. As already explained, to get where is the critical radius. It is here. Okay. So this one you read. So if you want to find the relationship between the energy and the R, or the gradient of the energy, is a graph. So once you have the relationship between the energy and the radius, when you dr, you can get the relationship between the critical size and the free energy. Means you take this equation, you differentiate towards R. So you combine the R, you group the R together, and then you no, it's a different entity. So you do this one, and then you do this one. Okay. So when you want to get the critical size, so at this point, you know that when you want to get the gradient or the maximum point of a quadratic curve, you do the dy dx equals 0. Right? At the quadratic curve, you do the maximum point dy dx equals 0. Same as this one. It's just that now your y is your energy, x is your r. Dy dx 0, you get your this point, you get your r position. Right? So when you continue to do your steps, dg, dr, or the energy of your radius, you get 0. Then you do this one. This one continue to carry on because this is a constant value. Then this one also carry on. Then you dr. This one become 3r squared. 3r squared, you rearrange, you get 12 over 3. But the r here become r star. It's become the critical radius because you want to find the optimum point of the curve. It becomes 0. So here also same. So this one become 8 pi r when you differentiate. Then but the r become r star. Again, the gamma here, this gamma is a constant value. So you just carry on. So by looking at this, you can find the r star. Okay. So you rearrange, you cancel the pi, you will get r star equal to negative 2. This one is 2 phi divided by delta gamma. Okay. So when you observe this graph, one phenomena that you observe from this graph, greater the degree of undercooling delta T below the equivalent melting temperature, there will be a greater change in the volume free energy delta G. The rest you read. This is another graph. On the left-hand side is delta T. The x is R. So you can see as the change of temperature will drop as your critical radius increase. So this side this side is your nuclear is stable, but if it fall within this side, then you have a smaller R star or smaller radius. Then they call embryos. So they will form here, and they will go back because they are too small, and then you continue to give energy, they will melt back to liquid. Okay. Rest you read. This is for copper, this equation for copper. R star, you can use the Tm is the melting temperature. You can use the heat fusion and the undercooling temperature, change of undercooling temperature, to find the critical radius. R star equal 2 gamma T HF delta T. So let's look at application of equation. Now you're given a few information. Calculate the critical radius in centimeter, so that you need to transform the index 10 power something into centimeter of a homogeneous nucleus. You know, homogeneous nucleus means you are dealing with pure element, so you give you pure copper. Assume delta T undercooling is 0.2 of the 2% of the melting temperature. Use data in the table below. Calculate. Then the second one is calculate number of atom in critical size nucleus at this undercooling. So you need to calculate how many atoms that are at critical size at R star. So you're giving this temperature, this table just now. So you can have the same if you already download the tutorial in chapter 4, then you can see this table. Huh? So on this table, you have heat fusion, you have surface energy, you have maximum cooling observed, and the freezing temperature also given. So how do we use that temperature? So here you will have Celsius and Kelvin. So calculation of nucleus is this formula, R star equal to 2 pi or gamma, okay, P T melting divided by your energy of fusion and temperature, right? So this formula you need to do in Kelvin. If you want to use this one, you need to do in Kelvin. So delta T undercooling temperature is given in the question. It say that delta T is 2% of the melting temperature. Right? So you are looking at copper. So from this table, the copper here. So in the freezing temperature or the temperature that start to start to freeze, right? So you need to add 273 to that temperature, right? Then you get your delta T equal to 200 something Kelvin. So you get the one of the term for the critical radius equation. And the constant value for this one is 177, is this one. Surface energy is given by I need to check the name for this. I think it's gamma or phi or phi. Right, this one. Right. So this symbol we are used for surface energy. So from this table is 177 10 power negative 7 joule over cm square. Your delta H is 18 something. Your H is this one, 1826 joule over cm square. And you substitute all the value, you will get R star equal to 9 point something, 10 power negative 8 centimeter. Okay. On this table, you see the parameter is in cm. Okay. So this is example. So if this kind of question come out, normally you will see a new table, but you're still seeing freezing temperature, heat fusion, surface energy, maximum cooling. But be careful on the unit that given in the table. Right. Calculation of atoms in critical size. So this, you see this one in the previous chapter when you learn about crystal structure. So again, you try to memorize what type of metals that fall into BCC, FCC, and HCP. In this case, copper fall under FCC crystal structure. So FCC under this one, copper. So your A is 0.3 something. Atomic radius, R star is 0.128. Right? So FCC crystal structure is what you see on the screen here. It's a phase crystal structure. So you have atom at the 6 faces, at the center of 6 faces. And then recall the calculation for relationship between A and R. Right? We take one of the faces to do calculation. Right? So we have A equal to 4R divided by square root of 2. Right? So this one you recall back. From this table, you have your R, you have your A. So it depends on which one you want to use. So you have two values to use. Okay, you have 0.36 for A, 0.128 for your R. Right? And then FCC, we all agree that we have 4 spheres or 4 items in the cubic. So we take all the information we know, and then we calculate the volume of a critical size. So volume of the sphere is 4 over 3 pi r cubed. You already find the critical size just now. You pull in the critical radius inside the volume equation. You get some answer, 3 point something. Again, here you see in the cm cube, in cm cube unit. Then you calculate the R star, this one referring to a nucleus, and you calculate the volume for copper you use A. A is the standard size of your unit cell. So it's 3.61, 10 power negative 8 cm cube. Okay. So where does this number come from? From this table. Okay. Use this one. Okay. Then the volume per atom. Volume for the cube will be for copper is 4 point something. You divide by 4 atom or 4 sphere. You get 1 point something per atom. Okay. So you have these three value you calculated. You calculated the earlier you calculate calculated the critical radius R star, then you calculate the volume of the critical size of the nucleus and volume of the unit cell of copper, and you calculate the volume per atom. So number of atom per critical size nucleus under this undercooling, you take volume of nucleus divided by volume of atoms. Take volume of nucleus that you form, this one, divided by this one. Okay, because it asks you calculate the number of atom in critical size nucleus, right? You'll get 300 something, 325 atoms that appear in the critical size that meet the criteria of this one. Okay. Yeah. So this example one is recalling all the fundamental in chapter 3 on crystal structure. And new terms that you learned today is the critical size. Okay. Next, this is add-on information. It's a definition of homogeneous nucleation. So sometimes it asks you to explain what is that particular term. So in this case, we are talking about heterogeneous nucleation. So this nucleation form in the liquid on the surface of its container and so on. It can be formed from the surface or any surface that it get contact with. It can get contact with the container. It's most easier way because you need to hold it in some way. So container, or if there are any impurities. Impurities means beside of its own. Right? If it's copper, then when copper meet with let's say nickel, so it will go and capture the nickel and form around the nickel. Right? And other structural materials that lower the critical energy required to form the stable nucleus. So here the keyword here is it go and capture any surfaces that it can get. Then when it capture, it will lower the critical free energy required to form stable nucleus. So this is how the nucleation happen. So for this one is for this one is for heterogeneous nucleation. Earlier one is homogeneous. This is for heterogeneous. Heterogeneous is not pure. You can say it is happen in a non-pure metal condition. So heterogeneous, when there's a alien body or a different body, can be container, it can be impurity or other structural material, right? Then it form nucleation. So this one is, let's say we form there's a container surface, then it will start to form solid in this way. Then there are some parameters used to define the process. So as we start by this diagram, and then we assume the nucleation, we start to form what you call this is a droplets, like a droplets. So there will be an angle of along the surface and so on. Angle is a contact surface and so on. Okay, the rest you read. Okay, the rest you read. What is important comparing to homogeneous nucleation? In heterogeneous, you need a lower amount of undercooling. means the change of delta T is much slower. You can imagine a liquid that contact with the cold surface, so it no longer need more high temperature or more energy to form the solid. So the energy will transfer to the contact surface. Right? Okay, so this is about orientation. So the orientation of the crystal is varies, means it change. Crystalline structure, is repeated, but you have a polycrystalline, means you have lots of solidified metals in a crystal structure. In metals, we call it grains. In metals, we call it grain. The surface between the grain is called grain boundaries. So later, when we talk about defect or imperfection, we will always recall the term called grain and the term called grain boundaries to define the type of the imperfection. Okay, the rest you read. Okay, there are two more terms to learn. Equiaxial grains and columnar grains. So for equiaxial grain, they grow in the same direction equally, or all direction equally. But columnar grains, column lah, column. Column is a long shape something, right? Long and thin coarse grain. They fall under columnar grains. When you do casting process, you will have a mold and you pour the liquid in. So where can you find the equiaxial grain is along the wall of the mold. So when you do your experiment, when you observe the sample, you can explain that at the wall of the sample, you are seeing equiaxial grain. So at the center, you are seeing columnar grains. So when you solidify at the surface, this one is the same direction of cooling. Then as you grow inside here, because of the space here, you will see there's a column shape that grow into the center of the surface, into the container, center of the container. Okay. And if you have this kind of shape of mold, the columnar grain, it grow perpendicular to the mold face. The direction is perpendicular, right? 90 degree to the surface, 90 degree to the surface. Okay, so let's watch a video on casting. This is in the industrial size or industrial scale. They pour the liquid just now and then let it cool and then turn into a step. Okay, I think the rest you can continue to watch at your free time. So there are some terms when you go into the factory floor. So the common shape in aluminum industry, they are called sheet ingots and extrusion ingots. The word ingot means they are the first, when you pour and it pour the liquid in and it start to become a shape. The one that comes into the process, that is called ingot. Okay, means the first, you can say the first output that you see from the cooling station. Right? So these are the process, right? This one you watch lah. So when you pour in metals, then into the mold, this is the stationary mold. So you pour in, and then there's the mold will always have a cooling mechanism. So in this case, they use water, and then they start to cool down the thing lah. Okay. Okay, so this is how they do. So this is I play some for you. So the top one is the cooling mechanism. So they pour in and they start to solidify, and then the bottom one will continue to just to bring down. Then all these will start to solidify. Right? Okay. So this is another production floor. This is a continuous casting of steel. So this is the process. So again, they have a liquid station, pour into a mold, and then it will start to cool down. As it's cool down, there is a fixture there to control the shape and the size of the metals. Okay. So next one is alloy. Alloy, you know, is a mixture of more than two kind of metals. Then we call this this kind of metal is called this is a composition. We start to do composition calculation for alloy. Okay. This one we start to do alloy. So first equation, concentration of weight percentage, M1 plus M2 times 100%. Right? So we specified the composition, or we call it concentration. We can either use weight percent or atom percent. So the first one, the first equation is in weight percent, or in the industry, you will see WT percent. Okay, so this one is very popular when it comes to assessment or your test or final exam. You will see it give you a weight percentage, then you calculate back the M or the missing M and so on. Or you're given the M and then you calculate the weight percentage. All right. So you know that this equation is only have two different metals. This equation, you only have two different metals. Because once you can find the first concentration for the first element, then the next one you don't need to calculate anymore. You just take, let's say you get 40% for the first element, next element will surely 60%, right? Because the total amount or total concentration is 100%. Or you can do the same calculation also. You just change this one to 2. If you want to find the second one, you just C2 equal to M2 divided by M1 plus M2. Okay, but the total is 100%. Atom percent a bit complex. Atom percent, A, T percent. Atom percent, you go for chemistry calculation. Chemistry calculation, normally you need mole something. What you do, you take number of mole for element 1, you take mass divided by the atomic weight. So you change the equation just now into number of mole if you want to calculate atom percentage. Okay, and the equation are used to differentiate the mass percent and the atom percent. Mass percent I use C, atom percent I use C prime or C comma. Okay, so what is important that you learn is that for mass percent you use weight, or you use the how many kilogram, how many gram. But when it comes to atom percent, you calculate mole. Okay, how many mole you have. You take mass divided by atomic weight. Atomic weight, you refer to the periodic table. Okay. Again, the atomic weight also 100%. Total atomic weight also 100%. So you only need to change the top one, or you just take, let's say C prime 1, you get 40%. The second element, you will get 60%. Okay, total 100%. Okay, the second one, C prime and okay. Then there's a conversion. Because you know that mass you can link with the mole, right? Let's say you're given a certain mass of an element, certain gram of copper, you can calculate in terms of atom percentage. So there's a conversion. So conversion, you need to, this one I already straight away I give you the final derivation answer already. There is a long step of converting here to here, but I straight away I give you the final derivation. So what you need is that okay, there are two. There are two. Okay, the first one, the first two that I give you, you convert. You are given the mass, you convert into atom percentage. All right. So C1 times A2, C1A2, C1A2, C2A1. Okay, so don't mix these two. C1 times A2, and this one is C2A1. What is A? A is atomic weight. Okay. And then what is C? C is your mass percentage. Okay. Do the same for the second one. Second one. Okay, the first one is C1A2. If you want to calculate the second one, you change the notation. You look for C2 and then you multiply by A1. Okay. Then if you want to do the reverse one, if you are given the atomic weight, you want to reverse back to the mass percentage. You change the C to C prime. Right? You change the C1 to C prime. Same with this one. This also C prime 2. Okay, you change the C into the atomic weight. Same with this one. Okay, I already, again, this slide I already skip all the derivation steps. Straight away I give you the final derivation steps. This equation is only for two types of alloying element. Two types. More than two, you need to derive from the base equation. Okay. Again, more than two is outside the scope of this module, right? Because you are not measuring in material. So if you're measuring material, then we go deeper. Okay. I think this slide is on the derivation. So you can read lah. You can read. It's a step from how to get the equation I showed you. Okay, you read this one. Okay. So this one show you the first equation from the base until here. You can repeat the same process for the another 3, another 4. Okay. Let's see how we apply the equation. Okay. So you are given composition in atom. Determine the composition is in 80% or atom percent of an alloy consists of aluminum and copper. So you are given the 97% of aluminum and 3% of copper. So you just apply the equation. So here, when you're given the percentage, so you use the equation that is given. So you are given with percentage, you're asked to calculate in atom percentage. You just choose the conversion equation, right? So you only need to find one of it, and then another one is 100 minus the first one. Okay, so here you just substitute. So you can choose which one is the first one, which one is the second one. So here, the first one I choose as aluminium. So C1 represent aluminium. A2 is my copper. So you change the equation. Then the A copper or atomic weight, you refer to the periodic table. Copper is 63.55 gram per mole. Again, this one refer to periodic table. You will sure seeing periodic table in all your assessment. Okay, you will sure seeing in your test 1, test 2, and final exam. Okay, so make friends with the periodic table. Then CAl is 97, copper 63, Al is 36.98 gram on the periodic table. Percentage of copper is 3%, 3 weight percent. Press the calculator, you will get 98.7 atomic percentage. So once you get the atomic percentage for aluminium, you should be able to find copper. Okay, so this kind of question will expect you to do 2 sets. So the first set is for one of the element, another set we just expect you to take 100 minus this one. Or you can do the same calculation, and then you still get the same answer. Okay, so what is the atomic percentage for copper? You have aluminium already. How many percentage for copper? 1.3%. Okay. So you can do the same. You can prove, you can do the same, substitute the same. You still get 1.3. Both steps give you same marks. You can do the long step, or you can just take 100 and get the answer. You still get the same marks. Okay, we have a short break here. Okay, short break. Hold on, I stop recording first.